So it's a pleasure to introduce you Richard Bowman from University of Glasgow. Richard works on microscopy and experimental automation, and he also transferred a number of technologies to commercial partners, but he's also the lead of the OpenFlexure project. Today, he's going to talk about how he learned about the Web of Things and how it applied to its OpenFlexure project. So Richard, the floor is yours. Please go ahead.
Okay, so I'll start with the Steve Jobs intro. This is not a toy. It's made of colorful plastic. It costs less than an Xbox and it fits in a shoebox. But nonetheless, it's a serious piece of scientific equipment. This is an OpenFlexure microscope, and it's a useful laboratory microscope that can be motorized and automated. So why would you want to print a microscope? For starters, it means we can integrate everything very tightly together, have it very small, fit it into places where a big microscope might not go. It reduces the cost, because a huge amount of the cost of a microscope is mechanics, and the 3D printing here makes it much cheaper. It also makes it easy to replicate, and I think this is where the project becomes exciting. The OpenFlexure microscope doesn't have many custom pieces, and the custom pieces it does have come off your 3D printer more or less ready to go. And lastly, because it's easier to replicate, because 3D printing and so on decreases the barrier between the digital design and the physical reality, people can make them, improve them, share those improvements back with the community. I usually put microscopy for everyone in the talk title, and perhaps it will help to understand where the projects come from. If I say, why does everyone need microscopy? There's loads of reasons: education, scientific research, inspecting products. But what's really pushed this project over the last few years is this guy. So this is a Plasmodium falciparum. It's the parasite that's responsible for giving you malaria. It lives inside a red blood cell, and that's what those kind of cloudy purple things in the background are. Malaria is a big problem. There are about 200 million cases of malaria every year and about 500,000 deaths. And that burden is borne disproportionately by children under the age of 5 in sub-Saharan Africa. The OpenFlexure microscope, because it's digital and automated, is really good for quality assurance. A huge part of the problem of using microscopes to diagnose malaria is it's very hard to check that it's being done competently. Keeping records would help with that. It also helps to train new technicians. So if you can look at an image on a screen, you avoid that classic microscopy problem of, I look down the eyepieces and I see the sample. You look down the eyepieces and you see a very enlarged image of your own eyelash. And lastly, and I think this is the most exciting thing, the OpenFlexure microscope is something that can be produced locally. And so our engineering partners and our healthcare partners in various countries in Africa, especially Tanzania, are able to make a relatively sophisticated modern microscope without relying on unreliable supply chains and expensive imports. I mentioned that it's easy to replicate, and that has led to this wonderful picture of all the countries in the world where OpenFlexure microscopes have been produced. And the vast majority of these have been produced with very little interaction with the original design team. And pleasingly, this map is always out of date. I think we're up to about 50 countries now. And the reason that it's been successful is that it's easy to build. That's good for scientific reproducibility. It's good for making it accessible to lots of people. And it's good because it means that people can hack around with it and the community is able to improve the design. Everything in here is openly licensed, so I have the privilege of not having ever to worry about what I can say to whom. We all have the permission to look at the source code and indeed to make them and sell them, and one or two organizations do. And lastly, we've put a lot of effort into this project to build that community. It started very much as something that we did in an academic lab, but it's very much bigger than that now. And I'll talk a bit later about some of the things we've done to promote that and some of the cool things that have happened because of that community. It wouldn't be fair to do a microscope talk without showing some pretty pictures. And so what we've got here is a 3.2 gigapixel stitched panorama of a pap smear. So this is from, I think, about 500 individual images taken by the microscope, and then we've scanned the stage around and stitched all of those images together. We're still working on getting rid of some of the stitching artifacts. I think we can do slightly better than this now. But that's the sort of thing that's possible if you have a microscope that is computerized and so able to move itself around, record digital images, and do a bit of processing. I'm going to treat us to that again. Right, this very busy slide is intended to give you a bit of a flavor of what the OpenFlexure community do with the OpenFlexure microscope. I've already mentioned malaria diagnostics, and so there are teams in Tanzania and Cameroon who are working on making them locally and using them for diagnostics, also using them for scientific research and educational things. We have colleagues in the US who have been using them for training medics, where they effectively function as whole slide imagers on a budget. And that opens a lot of doors, not just to building up great teaching resources, but also to doing telemedicine, where you have a slide scanner in one hospital and an expert in a different hospital who is able to provide a diagnosis to the first place without having to physically ship samples. And that opens up a lot of possibilities, for example, for people in one place, pathologists in one place, to support the healthcare system in a completely different place. And that's something that we're looking at piloting in the near-ish future. There's lots of other things. I think the last project that I'll highlight is a community group in Argentina that picked up the OpenFlexure microscope and has been using it to look at the soil microbiome, generating some data and helping educate farmers about the effect of different agrochemicals and trying to perhaps gather evidence to inform better farming practices that take better care of the soil. Right. All of this as an open project is enabled by vast reams of documentation. There's been a great deal of effort gone into our assembly instructions. In fact, we have now a custom build system that's spun out as its own open source project for managing the hardware instructions. But in order to make it useful, you need more than just instructions on how to build it. So we have a forum where a lot of the microscopy users are able to discuss it, share what's happening. We have a friendly website that tries to give you a nice place to start with the project. And we have lots of documentation of the software API. And I think that's really important for the more advanced users who need to go beyond what you can do with the graphical interface. And I suspect most of the people in this audience are going to recognize, I think this is the read.cli interface to our Open API docs. And yeah, that comes pretty much for free with the fast API backend we use, but it's incredibly useful. In terms of the front end, if I'm feeling really foolish and have some time left, I'll try and do a live demo of this for you. But we have a friendly graphical interface. This is provided as a Vue.js single-page web app, which is served from the microscope. So if you want to start using it, we have an Electron app that you can install on your computer, but pretty much all that does is MDNS discovery and then opens a web page that is served from the microscope. And that means that the client software is always up to date with the server-side software on the microscope. We don't have to worry about distributing the two things separately, which we tried once and it got really tedious really quickly. And the intention with this interface is to produce something that's fairly intuitive, fairly point and click, that has all of the features that our users need most of the time. But it doesn't aim to give you everything. It aims to give the features that are useful to someone who wants a microscope that works out of the box. I think a lot of the excitement comes when you start customizing it and integrating it with other instruments. Oh, I should say the demo there was click to move. So I'm clicking on the image and then I'm bringing the point that I clicked to the center of the screen. So it's also demonstrating that the relationship between the translation stage and the camera is calibrated, which is quite a useful tool when you're doing this kind of work. Right, now to the bit that is probably most interesting to this audience, which is the software architecture that powers it. And perhaps I should introduce this by saying that with the OpenFlexure project, we have quite a range of different users. There are some people who are microscopists, biologists, medics. They use microscopes quite frequently, but they don't build them, and they're definitely not software people. So what they want is to put their sample in and be able to very rapidly image it, perhaps even stitch together one of those big panoramas, but pretty much with the minimum number of clicks required. And if you need a training manual, it's probably too complicated. So the microscope itself includes a camera, which is the Raspberry Pi camera module, and a motor controller, which was based on an Arduino Nano. Now it's based around an RP2040 on our own PCB. And it's all tied together by some software running on a Raspberry Pi. And one of the big reasons we chose that platform is that it means that it can be standalone. You can plug in a monitor to the Raspberry Pi and you have everything you need. It works really pretty well. You could do pretty much everything with the innards of a mobile phone. But tempting though that idea is, I think there are quite a lot of problems with it when you try and do it at any kind of scale and when you try to get consistency between different microscopes. Because either you have to build a phone into the bill of materials, which makes it quite expensive and provides a component that is very, very stealable, or you have to rely on people bringing a phone, which means you never know quite what phone you're going to get. And if you want to leave it running and doing a scan for 3 hours, well, when was the last time you didn't look at your phone for 3 hours? So the Raspberry Pi is a nice platform to work with. And of course, it's got a network interface. So as well as displaying the interface locally, we can plug in a laptop with an Ethernet cable. If you're feeling really brave, you can try and do it wirelessly. And then you can pop up exactly the same graphical interface, but on a remote computer. And we found that's really helpful because some people just want an all-in-one box with a screen attached. Other people find it much more convenient to use a separate device for the interface. And then, of course, there are more advanced users who might want to use scripting in addition to the graphical interface. This is a slightly more detailed picture of the same thing where I've tried to break down the architecture slightly more. And there's a paper published that goes into a bit more detail on this. Essentially, on the Raspberry Pi, we're running a Python web server. In that Python web server is the code responsible for talking to the hardware, being the motor controller on the camera. That then exposes an HTTP API that is Web of Things compliant. It also serves the static web app. And so there is one HTTP server that is responsible for the web app and for all the hardware control. And on the Raspberry Pi, we also advertise the server using MDNS service discovery, which is how we make it simple for people to connect to the microscope just with an Ethernet cable. So we're not assuming that there's a DHCP server on the network, we're not trying to hard code the IP addresses so you can find it that way. But the MDNS service discovery seems to work really well. And then you can either use an Electron app, that's OpenFlexure Connect in this picture, or just a web browser. Obviously, if you just use a web browser, you don't get the nice MDNS SD discovery. But if you know the host name that it advertises itself as on MDNS for name lookup, you can still get that up in a web browser. And the bottom one, which wasn't on the previous slide, is you can also use this API from scripting. And we had Python and MATLAB client modules that let you control the microscope from a script. And one thing that I'll highlight that is perhaps not that obvious, but when you spend a lot of time working with scientific instruments, it becomes really important, is that you can have your GUI and your script running at the same time. I've lost count of the number of weeks of my life that have been sunk into re-implementing a GUI in the scripting language of my choice, because I want to run a relatively simple script. So let's say I just want to take an image, move the stage, take an image, move the stage. Implementing just those features is usually quite easy. But so often, I need to implement a lot more. I need a live feed of the camera so that I can get everything set up. I need the ability to control all the camera settings. And I can do that with the manufacturer's interface, with the manufacturer's software, but I have to shut it all down before I can start my experiment script, because of course the hardware will only talk to one process at a time. And oftentimes it loses all my settings when I do that. Wouldn't it be so much better if I could use the manufacturer's interface for all of the stuff that I do only once at the start of the experiment? And then the experiment code that I write just has to do the kind of the recipe, if you like, the protocol for that experiment, which is usually far, far easier to code. And with this network architecture, that is possible now, because of course there's only one process that ever talks to the hardware, which is sitting on the Raspberry Pi, and my client code can sit on the Raspberry Pi or somewhere else. But it means that I can monitor what's happening at the same time as running my experiment script without the need to build all of that monitoring into the experiment. What else have I written on this slide? I talked about headless or unattended operation. Essentially what I'm meaning there is that I can start an action that might run for an hour. And if I disconnect my client from the microscope, the action keeps running. And again, this is fantastic because a common bugbear in experimental labs is that Windows decides to update and your computer spontaneously reboots halfway through an experiment that needed to run continuously for a week. You can imagine the level of frustration and tears in the coffee cup that this produces. Whereas if you've got all of the experimental control embedded in the instrument on a nice, simple, fairly minimal Linux distribution, then when your Windows laptop is forced to reboot, you don't kill the experiment. And lastly, of course, it means you can have one computer, but you can control a whole bank of microscopes. And so if you need to scan lots of samples or run things in parallel, that's possible. And the load on the control computer is never that great because all of the real-time stuff is happening on the device itself. To give perhaps slightly more detail on the implementation of all this, we're now using Fast API for the Python backend. That's a recent change. The software has mostly been done using Flask as our web library, and then added in Marshmallow for managing types and generating schemas. There was Marshmallow JSON schema, and then a separate package to provide the OpenAPI documentation and so on. That stack was starting to creak pretty badly. We were still on Flask 1, And rather than go through an amount of pain to update everything, I decided it was probably a good opportunity to jump ship and try out Fast API, which I have to say has proven a good change. And we've also taken the opportunity to try and align the structure a bit better with the Web of Things. Previously, we had a kind of clunky extension system. And so the microscope was one thing, and then there was a list of extensions which had all the properties of a thing, but they were kind of sub things, and it all got a bit messy. So now there's only one kind of entity, which is a thing. And the microscope is a collection of things. There's no single microscope thing. There's one HTTP server, which then provides a whole bunch of things. I think there are 6 or 7 of them at the moment. So a thing in Python in our what I've called LabThings Fast API, the underlying library that helps make the Web of Things interface. Each thing is a Python class. An action is a Python function. You can decorate that, and then it turns into a descriptor, for those of you familiar with that parlance. Properties, again, they work like Python properties. And so if you were using that class in Python, functions are actions, properties are properties. It all feels quite natural. And that also means that the signature of the thing, which is responsible for all the kind of nitty-gritty hardware control, is pretty well the same as the signature of the client code that we generate based on the thing description. So it has the same functions, which are actions. It has the same properties. The client code is not yet nicely typed, but when that's implemented, because we're in the middle of a big rewrite of everything to migrate to Fast API, the types will all be the same. And that has been really helpful because it means that we can develop code in a nice, friendly, convenient environment. We can paste it in an IPython notebook, and we can work through our various actions that we want. And then that code pretty much copy pastes directly into a thing which runs on the server rather than in a Python client. And that's really sped up development. I'll briefly mention that Fast API has a nice dependency injection system where it uses the types of arguments to functions to provide things like data from the request context, or in our case, to allow things to depend on other things. So I can have an action that will find another thing in the same server and use that. And the dependency injection is quite a nice way to declare those dependencies just as function arguments. The front end, or at least the graphical front end, is all written in Vue.js. At some point soon, I will need to update that and migrate to a newer version of Vue, because again, this is all a few years old and starting to creak. The communication with the server is just done in Axios at the moment. We're only using HTTP, so there are no other protocol bindings yet. And I have sort of, it would be a stretch to call it a client module, but we have a couple of Vue components that are responsible for running actions and dealing with properties, both getting and setting. And so they provide quite a nice way to create a useful interface, but centralize all the code that deals with the Web of Things backend. I had hoped to switch to using Node Web of Things as a proper client module. I'll mention briefly that I was defeated by trying to run this in my Vue application because it made Webpack fall over. I think one of the dependencies doesn't play nicely with Webpack, and I've yet to find the time to debug that properly. But if any Webpack plus Node Web of Things ninjas want to come and help me out later, I'm all ears. This slide is a picture of one of the really fun projects that the Web of Things architecture enabled for us. And so what we did was we took an OpenFlexure microscope, we put it in a liquid handling robot, and then we connected it up to some other hardware and some machine learning libraries, such that we were able to design an experiment that did microscopy, that was doing liquid handling and sort of pipetting things around. Then it was doing some image analysis, and the results of the image analysis were fed back to inform what the liquid handling robot did next. And so it's properly kind of closed loop experiments with a bunch of different instruments connected together. And all of that is enabled by the fact that all of the instruments in question had a Web of Things style interface. The Open Trans pipetting robot isn't Web of Things compliant. It doesn't have a thing description, but it does have an HTTP API. It would be quite cool if we could persuade them to have a thing description. That would make this work even more nicely. Another fun thing enabled by the network API is that you can have clients that are in friendly scripting languages. And so this is an example using Blockly to control the microscope. And I think we initially developed this for school children, but I think actually there are a lot of people working in research labs who simply don't have time to learn a new language or learn a new API. But if they can drag and drop some graphical blocks to automate their microscope, then they will use that feature because it will help them get their research done faster. There's also a voice control module for the curious, implemented by the same guy who put this together. I don't think we've used that in anger yet, but it was quite fun to demonstrate that it's possible. And of course, you can have that as a client running somewhere in addition to whatever other interface you're using. So I was asked some questions in advance that I will try and answer before I go over time. I guess we learned about the Web of Things maybe 4 years ago when we were looking around for standards that we could build our HTTP interface on. So my postdoc at the time, Joel Collins, was the one who came across the Web of Things and also the Mozilla Web Things project as it was then. And those were really helpful in teaching us how to structure the API in a sensible way. What's it solved for us? Well, it gave us an obvious way to control hardware with HTTP. Reading about REST interfaces generally was helpful, but it was quite nice to have it spelled out in a bit more detail for hardware. Particularly because the thing description then provides a natural way to integrate the documentation with that. It provides cross-language and cross-platform hardware control, which is great because in most scientific labs, there are a variety of operating systems. People have a variety of different programming languages that they're comfortable with, and not tying yourself down to any particular one is really helpful. And in the future, and I'll have another slide on this if there's time, we love to link up existing control frameworks. And I think the semantic typing mechanism has huge potential for making that work. We've hit a few pain points. Firstly, I think the standard generally thinks that actions are quite short things. And some of them are, like if I click autofocus, that's done in a few seconds. But if I click create a 3.2 gigapixel scan, that could take an hour. And so there are allusions to the idea that you could do long polling, or you could return an object that you can poll in order to find out information about a long-running action. But I would have invented a lot less myself if that had already been spelled out for me. One thing I have come across recently is I'd like to have an action that tells me when it's done the first step and then continues running. That would be really helpful for a bunch of things. And I think there isn't really provision at the moment in the model for that to happen. I can have an event, but the event is associated with the thing. So if I want to take a picture and then process and save the picture, but provide a synchronization event after I've taken the picture, I'd like that to be tied to a particular action because of course there might be multiple actions running simultaneously, and it'd be useful to know that the action I've just started has now passed into phase 2. More detail on protocol bindings would be great. I think that's something the community is aware of and working on. But in particular, I've done a little playing with WebSockets. We've not used them much in Anger, but I'm slightly wary of sinking too much effort into inventing my own WebSocket protocol that then ends up being superseded by an official one. So I'd be keen to figure that one out. And then the thing description is great. The thing description, I think, is really the right documentation for your piece of hardware. OpenAPI is lovely, but you end up with lots of OpenAPI entries for each action, for example. And I think the equivalent of Swagger for thing description would really make it much easier to use and much more welcoming for someone to learn the API. And then lastly, I have invested a lot of faffing around in converting between JSON schema, which I have really good tools to generate, and thing description, which is almost but not quite JSON schema, at least according to my understanding. I am guessing that is something that might converge in the future. But at the moment, the bits of my code that I'm least happy with in LabThings Fast API are the ones converting between JSON schema and the data types of thing description. I'm aware that I'm probably pushing time now. I am very nearly done. But I'll briefly mention that there are a whole bunch of frameworks in use, some in Java, some in Python, some in C, for controlling scientific instruments. And I think a common problem is that they all try to come up with an abstraction for specific classes of instruments. So a class that will handle any camera or any stage. And the advantage there is that in theory, I can write my code for an experiment and then I can implement with whatever hardware I have to hand. And that's really useful. But the disadvantage is that it's not very flexible. And so if you come up with a camera or a stage that works in a slightly different way, it's very hard to crowbar that into the existing API. And of course, because most scientific software is written by scientists who have very little bandwidth for making good control frameworks, anything that tries to be universal is never quite as universal as it thinks. Most of these frameworks also tie you into a particular language. They often have quite onerous setup of the programming environment, and generally they suffer from the one process at a time problem. So if I'm controlling my thing with Micromanager, I can't simultaneously control it with the manufacturer's GUI, which is a bit of a pain. I won't go into any more detail on that because I don't have time. But how could we square this circle? How could we achieve interoperability without trying to persuade everyone to use one universal framework? So we'd need a standard cross-platform language-independent way to run actions, get and set properties, watch for events, and tie that all together with nice documentation. And that's exactly what the Web of Things standard does. So I think it's a perfect fit there. And I think the next ingredient you need is some way to gradually and in an opt-in, non-exclusive way align your instrument with a particular taxonomy of how a stage works, how a camera works. And I think with a bit of thought, the semantic typing mechanism could really help with that. It would allow my thing to say, I am a translation stage. It would allow you to say, this action moves the translation stage. This property represents the current position of the translation stage. This property represents the axis names, that sort of thing. And because you can have multiple ontologies on the go at the same time, it means my thing can then expose itself in a way that's compatible with multiple frameworks. And we can gradually opt in to more and more intercompatibility between frameworks without ever having to ask someone to sink a huge amount of time and effort into jumping over to a different framework. And perhaps it helps soften the blow to scientific egos. You don't have to suddenly put your framework into somebody else's framework. We're all sort of moving into a common way of communicating. You can still keep your framework. I think one thing that I'd love to be able to do, incidentally, is have two thing descriptions and figure out if one thing description is compatible with another. Sort of like duck typing for subclasses. I feel like it ought to be possible, but I've not got any code that does it yet. Right, I'm done. Sorry, that is slightly over time, isn't it? I hope that was interesting. I hope there are some questions. I'm going to stop now, and yeah, I'd be delighted to hear some feedback from everyone.